All right, wonderful. So thanks for making it here. It's the last talk of the day. Well, hopefully the last talk of the day. So I'm going to show you today what we've done with this exercise analysis app. So for those of you who haven't seen this before, the main motivation was to allow our users to just go to the gym and exercise. That's it. No interaction with no devices required. It would collect the data from the sensors that people wear, so they might wear a smartwatch like this one, and we would figure out what sort of exercise they've done. And so we started it. I had a first brief version of this at Scala Exchange, and then presented what I thought would be the final version at Scala Days in San Francisco. And so I thought today would be just a nice little roundup of how we run it and how it all runs beautifully in the cluster. And so we had this, right? We had a mobile app that collected data from smartwatches, and it collected data from heart rate monitors. It fused the sensors, fused the data from the sensors, ensured that the time aligns, and then it would send all these packets of acceleration and rotation to the server. So we made a request every 1.24 seconds. We submitted the exercise data to our Akka cluster. We ran quote-unquote real-time, so as it happens, analysis of the data, and given the input, we figured out what sort of exercise the user has done. And that we pushed back to the mobile, and the mobile, again, through Bluetooth connection, pushed it to the device, to the watch, so the users could check and provide feedback on the classification. We also stored all the events in Spark, so all the, in a journal. So all the exercise events ended up in, say, Cassandra for the imagination, for if you want to imagine it that way. And we ran a Spark job that attempted to find out more about the exercise. So what should the user do in the next session? Are they improving? Are they getting worse? And that was that, right? It was great. We had great fun building it, and it ran beautifully in our office. And then we gave it to our users in the gym, and they took it downstairs, where there is no Wi-Fi, where there is no 3G signal. And it was terrible. I have a few slides that illustrate it. It just was pretty terrible. Here we go. Right. So it was all wrong, right? Just don't do it. If you're ever tempted, I know network is not reliable, and I kept hearing it. And then when presented with the fact that network is really unreliable, it was a terrible surprise, because it worked beautifully in our tests. So it was all wrong. There were a few other wrong things with it. Namely, we suffered from significant data loss from the sensors. So these devices, through the Bluetooth connection, would sometimes forget to send data, which we knew, so we wrote code that handles it, and we padded the data with zeros, which turns out to be a terrible idea, and we'll see why in a second. We had strict network quality requirements, so our app didn't crash, so that was good. It went into offline mode, and it said to all the users, just keep on exercising, and we'll get back to you once you go online. And we then did, and we said to the users, okay, so 20 minutes, 17 seconds in, what did you do? And they all went, I don't know, you tell me. So it was terrible. We couldn't actually build our training data set at all. We were sending a lot of unnecessary data, because what I could do is this, and just stand still. That's clearly not exercise. And yet, by this time I was talking 10 seconds, those were 10 requests of nearly all zeros. So that was completely wasteful. And as I said, we had really insufficient feedback on the machine classification. So we needed the users to tell us what they've done right as they finished it. So as a result, I say user interface was not slick enough. It was actually all terrible. It was unusable in real life. So what do we do now? What did we have to do? We had to improve the sensor and signal processing. That's the code that runs on the phone. We had to have far shorter experiment cycle. So the idea that we have a go, we sort of have a theory that we could do this to the data that we receive, but we need to have the data, run the experiment, and write the code that actually implements our experiment. We were counting that in days, maybe weeks. We needed to go back to hours. So on the day of exercise, we needed to have a go. And we call this thing distributed lambda architecture with feedback. You're more than welcome to the name. I think it's a terrible name now that I've used it twice. But I'll explain what it means. So, typical lambda architecture is take the data, split it into a batch layer and a speed layer, and you provide a query layer on top of it. So in the speed layer, you attempt to analyze the data as it arrives very quickly. And then in the batch layer, you might store the data up and you might want to run some deeper analytics on it. That produces some results that might influence the speed layer. You have a query layer that gives you a view of everything that you've done. Okay. So, I've deleted the mobile and the web clients, ignore web pages. So, this original architecture, if we overlay the lambda architecture on top of it, here is what we had. And so we had the signal processing, we had the classification in the speed layer. That was the Akka cluster that was doing it. And then we had the Spark side where we had some deeper models. So that's those images. We try to improve the models. We try to, have regressions, make predictions about what the users might do next time. As I said, that didn't work. So we have this distributed lambda architecture. I say distributed because we've divided the speed layer. And we run the speed layer on two completely different computers in completely different networks. We run all the signal processing. We run all the classification on the mobile, and then we only provide the positive and negative samples to the server. We might do some further classification on the Akka side, but that's no longer in real time. There is no need for a feedback. The data still ends up in a journal, and we still have the Spark code that runs the analysis. So if you think about it, we were right. It's just, it didn't work. But the stuff still needs to be done. All the DSP, all the learning still has to happen. We just shifted it to different computers. Now, as a result of that shift, we had to write more C++, unfortunately. So I'll show it very briefly. I know this is a Scala conference, so I won't stay too long on it. The motivation, if anyone's tempted to write code for mobile devices, that's low level enough that you want to share between Android and iOS and maybe Windows Phone. Who does Windows Phone? Excellent. All right, okay, so ignoring that, we've written this code in C++. We have an independent multi-platform code base. We can write it on our big computers, CI/CD it on big computers, and then we can build the same thing for iOS, we can build the same thing for Android, and just provide user interface shells around it. And in C++, being C++ code base, we can use all the favorite libraries that are out there. So OpenCV turns out to be a great way to give us all the linear algebra and lots of the machine learning stuff. We don't have to write it ourselves. So that's cool. We have smallest possible on-device code. We have sane development tools. So if you want to go and see the guys downstairs at JetBrains, AppCode, CLion, over Xcode anytime. So here's what we have. Here's an example of an exercise, and I'll have many more. This is raw data as it arrives from the device. One of the first challenges was, well, how do we tell exercise from no exercise? And it turns out that exercise, given our measurements, is a nice repetitive movement. And given some context around the exercise, and you'll see in a demo, we can define what this period should be, and we adapt the period of exercise for every user. So when you download the app and you train it, it will run for you. It will work for you. If you give it to your friends, it will not work. Just won't classify it, won't even detect it. So you start off with something really simple, and you just say, yes, you got it right, no, you got it wrong. And over time, it improves what it does. So that's kind of cool. So, I mean, typical example, some frequency analysis. So what is the period of the movement? And if it falls within, so this, the axes are actually fairly blurred, but this is about 1 second period. So you say that's actually consistent. This is some movement with 1 second period. And so we'll take this whole block and say, this might be an exercise. That's what we throw away at the classifiers and say, well, what is it? Now tell me. So that's one example of the stuff that we do. We write some Octave code as an example, because again, it's an experiment. We get the data, let's just have a go. And so we have a really high-level language that we can have a look at. Here's the terrible example of padding. That's what we used to do. So, nice movement, and then this zero stuff. So we had to fix that as well. Again, if it's just a short period, doesn't really matter, but when it stretches, it really damages all of our DSP work. So what did we do? I mean, what could we possibly do about it? Well, I think we all remember from physics, that things moving under some acceleration behave in a predictable way. And copying shamelessly from Wikipedia, we were able to use the Kalman filter. So electrical engineers, yes? No? Okay, well, you should cheer. This is actually good stuff. It allows us to predict what might happen in the next phase. So given some history of movement, what will be the next thing? So we have no data, or now what? So let's predict where this thing might be in the next 50 milliseconds. Again, we didn't write this stuff ourselves. It's all OpenCV, right? We just sort of had to know how to use it, which was great. So we were able to write this code very quickly, and again, run an experiment and see that it works, and do the frequency analysis. We also had to reduce the amount of data that we have. So instead of taking every point in the movement, we squash it down. Let's just have bands, so we approximate the signal. And again, depending on how wide we want to become, we have so many data points left. And so now I don't want to scare you, right? I mean, this is just stuff that shouldn't really belong at Scalad. Here's Xcode, and Objective-C, and Objective-C++, and Swift. None of this matters, really. It's just stuff that has to be written. You're more than welcome to it. It will all be it's all on GitHub. You can have a look if you want to. But hopefully now you can see what the little computer does. It actually does a lot of work for us as it happens. It's the only, by little computer I mean the phone. It's the only thing that has immediate connection to the sensors, the only thing that can provide this immediate feedback to what the users are doing. And it sends the data, but by now the data that's coming into our Akka cluster isn't the raw data. It's not the acceleration and rotation. It's, here is a block of data, here's 10 seconds worth of movement, and I've analyzed it, classified it. This 10 seconds of data of movement that I'm sending you represents this particular exercise, and the user has confirmed it, that it is indeed the case. So the stuff that ends up in the journal now isn't data acceleration values. It's acceleration values plus confirmed results of our classification, or rather the results of our classification plus the confirmation, yes or no, from the users. That's what we persist in the journal, and that's what we get to analyze in Spark. So this hopefully explains how we might go about building models for each individual users. We now have the data. We can retrain stuff. So if you think about, I mean, underneath all the C++ code does libsvm. So we can build new models for libsvm. When the users log in, they can download the latest model we have for that particular user. And we can, again, run a Spark job. We don't do now. I'll take a pull request. We can take all the data, retrain the model, and check that the new results are actually better, or rather they match what the users have told us. Maybe we invent a new thing, new feature. We can identify intensity of exercise. But anyway, that remains to be implemented, and I don't want to bore you with it. Now, to give you an idea of what real exercise is, so I haven't taken, this is unfortunately my exercise for what it's worth. I have all the training data for you, so you can have a look, but it's my exercise. I didn't want to share any of our users' exercises. That would be sort of wrong. They didn't give us permission to do that. Here's one. Here's another one. You can see that they are nice periodic movements. And here's another one. And another one. In fact, here is an entire exercise session. So ignoring what they are, I don't even have to tell you, but you can probably spot that there are about 5 different exercises just by looking. I mean, we can do that because we're humans, and that's kind of cool. Getting a computer to understand it was slightly more difficult. But then again, looking at all the traces that you have, you can probably think about very simply what features do we want to extract from the data? What will form our feature vector to be trained with libsvm? So it turns out that at the minute we're at about 25 dimensions for our feature vector. There'll be more, there'll be less, we don't know yet. But here's an example of what's coming from the accelerometer data. So, coming back to this, we've covered the mobile. We still have push notifications. In the future, we plan to add some social networking, but it's a solved problem. I'm not interested. So if anyone wants to program another Facebook, you're more than welcome to, right? All right, let's take a look at our Akka cluster. So, data that falls in from the data. We have some sort of exercise programs, the Jedi training camp. We have the exercise data that's being pushed from the device to our Akka cluster. So that's the result of classification plus all the data that gave us that result. And we have user profiles, boring old stuff. Now, we process it and we save into our journal the exercise data, alongside other stuff, but the really important events we persist are the exercises. Slightly deeper into it, right? So we have the watches, ignoring some rich clients. We have a load balancer, we have a couple of nodes. So we have, if you like, two microservices. A profile microservice that has usernames, passwords, first name, last name, age, that sort of business. And then we have the exercise microservice that records the data and essentially in this new architecture just saves them in the journal. Remember, all the classification happened on the phone. We don't have to worry about it. Just it has to end up in the journal. And then we have at the bottom, so that's our distributed state. So this is a cluster, and we have many nodes, and we've distributed this state, all the user profiles, and all the exercises for all the users. And now at the bottom of the cluster, we have distributed computation. So one of them is really naive Apple push notification. So there's a service that I can send a message to and say, deliver this to device ID, blah, and it sends a push notification. And then I have this final component, which is our Spark analysis. It's another distributed computation. It reads the data from the journal, and it delivers results back to the main cluster. And we'll have a look at what it actually is. So if we peel another layer of the onion, this is usual stuff. I say it in a horrible way. If this is unusual to you, just throw something at me. But a spray service talking to, in the case of user profile, a user profile processor, which is an instance of a persistent actor. We have one per node. So this guy is supposed to do some initial validation. And by that I mean, so it receives a command, like user wants to register. Well, it has to check, can I even register this user? And in our simple system, we will refuse to register duplicate usernames. That's the only check we'll ever do. If the user profile processor is happy with the result, it takes the command, it generates an event from it, persists the event, and it delivers it to now a user profile actor. So this is a cluster sharded actor, and we have one instance of user profile actor per user. So we keep the state, this state, right? Username, password, first name, last name, weight, age. We have that as a state in the user profile actor. And the user profile actor is now sharded across the entire cluster. So we can scale. Obviously, when we are the billion-dollar startup and we have hundreds of thousands of users, no, okay. Maybe not. Exercise service is a similar story, except even the user exercises processor is now a cluster sharded component. We have an instance of user exercises processor, the thing that receives the commands, per user. When the user is exercising, we have an instance of that guy. It persists the events, maintains some state, but we have some pre-computed views hanging off it. So that's the main difference. There are some questions that users typically want to know, and we can pre-compute them. By that I mean the user exercises sessions, the user exercises programs, the user exercises statistics keep up with the events that the user exercises processor is writing, and they mutate their state. So the state in, say, the user exercises statistics is how many exercises of this kind has user done? What's the user's favorite exercise? What is a typical weight? And we can have that pre-computed, rather than going to Spark to run some complicated query or complicated computation, because that would take a long time, or potentially a long time, and we'd have to program. And at the bottom we have snapshot and journal. I still haven't decided whether the rubbish bin is a snapshot or journal. Depends on what data you have. Right, okay, so to code. The profile service, again, this is a neat spray API. I won't go into the details of it, but you can see we have a RESTful API, we have in this particular case, profile service has URIs that begin with user, and then we can post user to register it. We can then get a user's profile by ID. You can set and get it, of course. We can set and get user's image. We can register an iOS or Android device. That requests to these guys end up as messages to the user profile processor. User profile processor, being a persistent actor, makes us implement these two methods. We have to implement receive recover. We have to implement receive command. Now, receive recover runs when this actor is created. So suppose the node that this actor was running on has died. Well, okay, we are a resilient system, right? So we can create a new one, new user profile processor. When we create a new user profile processor by that IBEAN system.actor_of, it starts in this empty state, default state, whatever we initialized at the start. We need to get it to the state that the actor that died was in just before it died. And we do that by replaying all the messages to it. And we handle that replay in receive recover. Receive command is when things are just running normally. So you send a message to the actor, and off you go. It receives a command and does something. So let's have a look. What state might this user profile processor have? Well, we need the user accounts. We need everyone who's registered in order for us to do the validation. So the simplest case, someone wants to register, and I already know the username. Well, that's a nice, neat solution, isn't it? So I just check, do I have the username? If I have the username, just reply 400 something to the user. This is a terrible request. Go away. I already have it. If the thing succeeds, so the previous case didn't fire, now I have a valid, as in new email, I generate an event that ends up in the journal by calling the persist method. I send this user account registration detail to now newly created user profile actor. So this user profile, an instance per user, got created somewhere in the cluster, and I'm sending it the user registered message. Mutate my state, save a snapshot, and reply to whoever's calling me with, this is the UUID, right? So you sent me username and password, and I'm sending you UUID. It all worked, HTTP 200. And this is great, until you have many nodes. Remember, this is a user profile processor, lives one instance on every node. And so when I register on the leftmost node, right, so the load balancer decides to send it to this guy. Is it on the left? Yes, it is on the left. Excellent. I mutate my state, save the message, save the snapshot. Brilliant. All worked. Now, second request goes to the middle node. And my monitoring decides that I have too few user profile processors. I need to grow my environment. Okay, that's kind of cool. I create a new node. That new node runs the receive recover message. It recovers from the state that the leftmost one has saved. And it's all good. It works. I have the same state in the middle as well. What about the third scenario? The arrow is in the red, so that's not good. Well, this user profile processor existed. It was running. I've mutated the accounts on the leftmost one, but of course the rightmost one doesn't know about it. Went to a different request. So now I could potentially register two users with the same username. I need to fix it. Well, I can create this bus that every profile microservice subscribes to. And messages I'll send on that bus will be, differences. So every time I register someone, I'll send to the bus a publish known accounts. So one user profile processor has registered an account, and then it says to all the others, look, I've done this. Check your state, synchronize. And then the others, so this is some other user profile processor that's not self, when it receives this user known account added, it mutates its state. Now, no talk, I couldn't continue without showing the user profile actor. This now receives, remember, this is now sharded. Now, I glossed over something really, really fundamental. Who here has heard about the CAP theorem? Okay, who hasn't? I mean, this is simple, right? So the system that I've shown you just a moment ago is, for some period of time, inconsistent. There's nothing you can do about it. That was my decision. So there can be time when the user profile processors aren't all synchronized. They see inconsistent state in the cluster. And I've done that because Again, in my megalomaniac vision, this will be like 10,000 registrations per minute. If I have duplicate registrations like 2, that's okay, I can just ignore it. It's a user interface problem. Simple, right? But it highlights the fundamental problem. I had to make a decision. I could become consistent and then sacrifice either partition tolerance or availability. I've gone for availability and partition tolerance. And so consistency went away. Okay, never mind, turn it back to the user profile processor. It's another persistent actor. The pattern that you might notice here is that I change state. So I start by not register. This is a template, blank user profile. When it receives the account message, it persists it, mutates its state, and context becomes, it switches behavior. When it is registered, I can reply to all the normal messages like get account, set account. User exercise process, it's the same pattern. Right? I receive messages, I validate them, generate events, and they end up in the journal. So in case of user profile processor, let's focus on just something really, really simple. All that we're going to do for the demo is show an example where I receive the classification results from the mobile, so an entire exercise resistance session, and I'll save the event, and that's all I'm going to do. I'll just reply to the user, yeah, that's okay, we've got it. We'll get back to you later. Something will happen. In case of suggestions, well, let's not even show you the code. The code you'll see in the demo is a print line, but it demonstrates the same principle. An event, a command arrives, do some validation, generate an event, and once I've persisted the event, I'll never forget it. It will always get replayed. Either here, when I do the delivery, or if I've made a bug here, I can make a change, deploy a new version, and have a new version of whatever views, whatever processors I have, and have that old event replayed to them now with new code. Okay, so hopefully this is beginning to make sense. We have a mobile client, collects the data from all the sensors. The important stuff really is the exercise, but even the training programs and the user profile fit in the same pattern. We have an Akka cluster that maintains distributed state. I have some distributed computation, and we save the events to the journal. Once they are in the journal, we might do something interesting with them. On the Akka side, the interesting stuff is we'll never forget them. We can recover. On the Spark side is, well, let's see about that. So what do we do in Spark? Well, this will be interesting. So the green stuff, it's all done. We all understand that. That's cool. The red stuff, we would like to read all the events from the journal and then discover something new, make predictions. That's why we're bothered, really, to construct it. There might be some complicated queries that we want to run as well. I'll give you a few examples of the things that we've done. But before we do that, we need to figure out mechanics, really. So this looks really cool, right? So the Akka side calls persist. We're given some instance of a case class, and that ends up in a journal. And I'd like to have code in Spark that just sort of loads it and recreates the same case class, and I can run anything I like on it. But there's a monster in here, and the monster is called serialization. Now, in this particular app, the Akka cluster is running Scala 2.11, and the Spark code is running Scala 2.10. And all sorts of interesting things happen when you do that. So we need to find serialization that is, fast enough, that's stable, meaning if I change tiny detail in my case classes, it should still hang together. And the killer, particularly when it comes to Spark, is it wants to be compatible. So I cannot have, there's an excellent Creo serializer for Akka. Works fantastically well. It uses Creo 3. That doesn't work in Spark, because Spark uses Creo 2 point something. You can take some other library. You might go, okay, you know what, I'm going to do protobuf. Let's do protobuf. And you're in the same ball game. You can say, I will use Thrift. Same stuff. I'll use Avro. Same stuff. So we have tried all of them. Well, okay, not all of them. That's exaggeration. We've tried protobuf, we've tried Avro, Thrift, and Creo. We settled finally on Creo and Chill. So this, at the minute, as in a couple of days ago, is stable. It runs in Spark, as in it allows me to see the events that I've persisted from the Akka side using Creo, and it allows me to read those very same events as instances of the same case classes in Spark. So that's one of the troublesome things that you have to do. Now you could say, oh, Spark is coming to Scala 2.11, this will all go away. I sort of tend to look at it as a bit of a smell in my architecture. That I'm now, if I'm too tightly coupled to a specific version of Scala in two completely different systems, that makes me nervous. Not to mention that Java serialization is just painfully slow. All that you have to do is add a field, and it's all broken, and serial version UUIDs, aha, come on. That sounded Dutch. Anyway, so this is fixed, right? Events come in, they end up in the journal, we read them in Spark. How do we do it? Well, we'll take the Spark Analytics plugin. Now, this is just a really, really simple example. So, with a couple of import statements, namely import Cassandra underscore and import Akka Analytics Cassandra, we can now get to the event table. So that's the journal that we have written in Akka, and we'll for each print line. Right, so this fantastic Spark job, when you submit it to a Spark cluster or even just a single node Spark, connects to the table in Cassandra that contains all the messages. Every time you call it persist, that ends up in that journal, and we can read it here. And for each print line, I mean, okay, so it doesn't really predict much, does it? We need to build something that allows us to make predictions. And, you know, just to keep within reasonable time frames, how about we predict, oh yeah, that's how we run it. So we assemble a jar, we submit it, single node Spark. Right, nothing too complicated. If I ran that, it would just dump all the messages in, and we'll take a look. So let's make a prediction, right? And let's do something really, really simple that we can, you know, pull together in the next 5 minutes or so. Let's do linear regression, right? Everyone does that, everyone starts with it. So let's predict intensity. We have intensity, the users tell us how hard they've worked, and we can say, well, how hard should they work tomorrow, the day after tomorrow, and so on. So this is a nice and simple job. Let's just do it, right? So in the grand scheme of things, all that we have to do is get the users from the journal. So all the events, remember, this is per user job. Every user will have different intensity. And then every user will do different exercises with different intensity. By that I mean different muscle groups. So someone likes to do legs, someone likes to do arms, and what have you. So we need to just not predict overall intensity for everyone. It needs to be intensity per user. It needs to be intensity per the muscle group, if you like, that they are training. Not to make it too complicated, we get all the users, and then we will take for every user ID, we will calculate, we'll predict the intensity. What should that particular user do in the next session? So tomorrow, and the day after tomorrow, and the day after tomorrow, and so on. And then for each of those, now that we have the results, right? So we have a list of tuples, user ID, intensity, user ID, intensity. We need to send them back to our system so that the users, when they log in, can see it. And so we'll just make a simple RESTful API call. Remember, this is running somewhere in the Spark cluster. I can't write to the journal. That might even be read-only. I need to get that data back to my original app. Well, I already have this RESTful API, so I can use the very same thing. Same case classes, same JSON marshallers. It's really simple code. So that's, in the grand scheme of things, what we're doing. Okay, how do we get the users? So this is one last bit of mechanics and sort of Akka Spark connector related stuff. We need to, the input that we get are all the messages that Akka has persisted. And it persists this structure called journal key that contains the identity of the actor, the persistence ID, and a few other bits, and the X, the payload. So all that we want to do from this line of code is to extract the user IDs. Now, how can we possibly do that? Well, remember that user exercises processor is an instance per user. So its persistence ID ties it to that specific user ID. And so I can do this. I can just pull it out and have the user ID. So I'm holding this user ID, really a Java UUID of the user that has done that exercise. And now, I don't actually expect you to read all of this stuff. I can sort of window train my linear regressor, and then I can make predictions. So over however many days I want to predict it, so I've trained the intensity model here. So this gives me the basis for making my predictions, and then I've said how many days do I want to run this prediction for. So I'll say, okay, well, I want to predict the next 2 weeks. That's probably good enough. So I'll run these windowing functions, and I'll compute predicted intensity. That's all there is to it, and I'll spit out this list of suggestion.intensity, and I'm done. But you know what? Let's have a demo. This is getting a bit boring. I don't like slides. So let's do a user interface demo first. So let's see if this all works. Yes, all right, excellent. So this is going to be troublesome. Bear with me. So I'll run the app. Nice and simple. Okay, here's the iOS version of it. Remember, this app does the No, don't do that. Remember, this app does all the classification in real time. I actually take off my watch. That's my sensor. I have trained it specifically for Scala days, so don't worry. It will recognize this exercise. It's patently not the exercise that we're going to be doing, but for the show, right? You should be able to see that this is just a plain watch, runs the software on it. It will be mirrored, so you'll have to use your imagination. Nevertheless, right, let's run this. Scala days demo. So it will connect to the watch. It will run the code on it. It will synchronize time. So what you can see here is that the watch will tell me what I should be doing, and I can even see a little sensory view. This is what it's recording. If I turn it, you know, the axes will flip. There you go. So this is the stuff that comes out from the watch, just so you know. All right, so never mind that. So what I'm going to do now is move the watch. Now this is where you get the show, because I won't get to see what's on the display. Nevertheless, I'm doing movement that's consistent with exercise. This is at the DSP level. I'm predicting what it might be doing. This is now exercising. I'll stop, like so. It runs the classification on the device, and it gives me the result. So imagine, this is in your pocket. And now this watch says, okay, this is what you've done. If you just leave it, it confirms it, which was my positive sample. So the movement that I've done was indeed whatever exercise that I've done. This, together with all the data that I have recorded, gets submitted to the server as we made these predictions in our iOS code. The user said, yes, that's actually true. And we move on, right? Nice and simple. I can do the same thing again and again and again. Never mind all that. So, there you go. It just displays it in a fancy way. We've done one exercise with that intensity. That event, entire exercise resistance session, I'll turn this off, this is getting disturbing. Entire exercise resistance session ends up on the server. Now, how does it actually look like? Well, there we go. We have the exercise service. You can have a quick peek at it. So what I've submitted is this, an entire exercise resistance session. Well, what does that look like? It contains the session ID. It contains the session properties, as in what am I going to do. It contains all the exercise sets that I've recognized. So this is what the user has confirmed. I have indeed done exercise blah. It gives all the examples. So the examples are the positive and negatives. So the user has really confirmed that this movement was exercise blah. Or the user has used these buttons to say, actually it wasn't that, you got it wrong. So we have all of that. And we have deviations from exercise plan. So when I was saying about, you know, the interesting jobs that we run, one of the jobs that we ran was, one of the questions that we had was, where do users typically deviate from their exercise plans? You go to your personal trainer and the trainer says you should do this, 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 and that. And then we ran it, we observed what the users were doing, and the question was, where are they just ignoring the plan? And we found that there was one particular exercise where nearly half of the users just did the different thing. And we thought, well, that's suspicious. I mean, what the hell is happening? So we went to the gym and we sort of had a look, and they didn't have enough weights. So the users went up to the rack and just went, oh, okay, well, I'll do something else then. So this is just a trivial example of, but this is an interesting thing that you can ask your Spark job to run. So let's do just that. We'll have final hurrah. I'll run the entire service. So this now runs the cluster, starts the microservices, connects to Cassandra, and I have a job in Spark, this regressor that predicts that calculates the suggestions. So this is in our user exercises processor when it receives the suggestions. It's a print line. We don't have to worry about anything just yet for the demo. And here's a Spark job I prepared earlier. It does the linear regression that you've seen a moment ago. Now, what we should see when it finishes is a suggestion for that one user. We'll have to give it some time. We have events, and it needs to distribute all the computation, and it needs to talk over the network, so fingers crossed. This is running, thinking. Request succeeded, and here we have it. So we have a prediction for tomorrow. Today is the 9th, and we have prediction for the day after tomorrow, and so on. And here's the prediction. So the user should do back exercises with this intensity. And on the Friday, the users should do, okay, well, this is not a good user. I mean, this is slagging off, really. What can we do? Excellent. That's how it works. Now, in terms of the data that you receive, here's one I prepared earlier again. This is what our quick analysis looks like. So again, we have the raw data, unfiltered, nice smoothed out version of the same thing. They look at the frequency components of it. This is how we construct our experiments. Let's just have a go. So, we are nearly done. I have one last thing to do. Not the demo, not the Q&A. That's too early for that. Let's do one more thing. And that's this. So this is the GitHub repo. Don't tell me the Wi-Fi is broken. This is looking really, this was going to be the golden bit of the talk. Come on. Conference Wi-Fi, be good to me. Establishing secure connection, this is not looking good. Network is unreliable. Boom, boom, boom. Yeah, very good. All right, well, I won't. There we go. All right. Okay, here we go. So, the last thing that I need to do is, of course, that. Yay. So, the Akka server that goes in, that's out. So, this gives you the cluster pre-classification. That's the C++ code base that runs on the mobiles. You can build an Android version. You can build an iOS version. Whole bunch of C++. Network is unreliable, I know. This is terrible. I am really trying, you know, I'm trying to be good. Oh, come on. So, let's see. I can't even... Now, this is not good. There you go. All right, so just to give you an idea, this is nearly all C++, little bit of MATLAB. You have the training data. So I've been good enough to give you all of this stuff so you can knock yourself out. My exercises, you know, for better or worse. Right, so that's the second one. Over pre-classification. I understand. Next up is the analytics. So that's the Spark job. Nothing too complicated. You'll be able to have a go. So clicking settings again, and it still doesn't work. Let's try again. This is just not good, really. I mean, you'd think that this conference would be the open source thing, and they'd say, I can see that you're publishing these things under some... Yeah, it's just... This is just not good. Anyway, I won't bore you. I'll get it done as soon as we're ready. You will, as soon as we're out, see, this is just terrible. Any questions you have? What you'll also get is the analytics. You'll get the Pebble code. You'll get the mocking framework for the Pebble code. The one thing I'll keep behind is the infrastructure code, because I'll be talking about that at Scala Exchange. I'll be showing conductor R and all the mesos and all the marathon code. And we'll rack up some AWS bills in December. So we'll see about that. So that's one thing. You're not getting everything else. I'll go through it. I won't bore you now. So, with that, any questions? Hi, you.
I saw that in the persistent vector you save a snapshot on every event you persist. Why do you save a snapshot on every event and not once every
Right, got you. It's not necessarily on every event. In the user profile processor, I save an event on just registration. It's just the only thing.
You also save the snapshot.
That's the only time.
That's the only time.
That's the only time. In the user profile, I only save a snapshot when I become registered. And then once it's done, I'll leave it to Akka. So all, you configurable number of messages called save snapshot. These are what I like to think about big sort of timelines in my actor's life cycle. Okay.
You said you didn't want to do the start-stop thing. You just want to have it always on and, gathering your sensor data. Do you know what that does to your battery life?
It's not, I'll say it's not too bad. The Pebble Watch survives. So the Pebble Watch without the code, so I'll start with the simple stuff. The Pebble Watch uses particularly battery-heavy API to send the data in quote-unquote real time. The code on the mobile attempts to enter as deep background mode as possible, so it just reacts to the Bluetooth data. So the only thing that we have to do is concatenate enough of the Bluetooth data, and then we run progressively more intensive computation. So on the first stab, we say, is it moving at all? So, nice average, is it beyond something? That can be done really, really quickly. Second thing is the DSP work. Is it periodic enough? Is that look like an exercise? And then the SVM work.
So the less you move, or you put down the...
Right. Yeah, if you just leave it like that, we practically don't do any processing at all, just the I/O. As soon as you start moving, we'll do some DSP work, saying, could this be an exercise? And if you do nice big periodic movement, it's only when you start moving in a different way or stop. That's when we run the entire classification. It's still heavy, but compared to the previous version which kept even the data radio on all the time, it's massive improvement. Sure.
Would you love a non-technical question?
Of course.
What's the business case? I mean, don't do it.
There isn't one. It's fun.
It's really fun.
Yeah, it's just fun. There could be business case. So we're talking to the runtime verification group and feature extraction group at Manchester University. We're interested in physiotherapy. I think that's actually really quite cool. So the question is, what should we suggest to the user? Now that we have this real-time feedback and it has sensors, so it sort of vibrates as I finish, is there anything that we can do to the users to say, well, now do this, or how about one more of this? So yeah, we are pursuing that. We had a go at it in the open source version, or in the previous version that unfortunately was broken. To do that runtime verification and feature extraction, we, again, just for pure fun, because it was possible, wired in an SMT theorem prover, a CVC4. Now that I am not compiling for the phone, absolutely not. So we'll need to think about a more compact view of it. The question is, so we're trying to implement some linear time temporal logic. That is to say, suppose you observe this exercise now, then for the user to have some medical benefit, we need to observe this movement in some bounded future. So in some finite time, we need to see this followed by that. And that's actually quite neat to do in SMT provers. But whether we're going to do that precise thing, I don't know. But physiotherapy is certainly very, very interesting. Anyone else? Well, let's have drinks. I'll be around. Welcome.